You may have heard of decibel meters or decibels. It's a measure of the loudness of sound. And it's a remarkable fact that our ear is so sensitive that it can hear extremely faint sounds, and it still doesn't break. The eardrum still doesn't break when the sounds are really, really quite loud. So we're going to quantify how well the ear can hear sounds using the decibel scale. So for a 1,000 hertz tone, the smallest sound intensity that the human ear can detect is about 1 × 10⁻12 watts per square meter. And I'd like you to please consider how tiny that number is. What's 10 to the minus 12? Well, 1 millionth is 10 to the minus 6. So this is a millionth of a watt per square meter. 10 to the 12, 6 plus 6 is 12. That's a very, very small sound. On the other extreme, you can actually, for a short amount of time, you can hear without breaking your eardrum pitches where the sound intensity is 1 watt per square meter. That is a sound intensity that's a million times greater than the very faintest sound you can hear. And I leave you to marvel at this amazing instrument that we've been given, our ears. It's just amazing to me. This is one of the most fantastic facts about our body. So it's kind of hard to compare with these numbers being so different, a factor of 10 to the 12 different. It's easier to do math if we come up with a logarithmic scale that kind of compresses that distance into a manageable amount. And that's called the decibel scale, and it's called the intensity level. So you said, well, we already defined intensity. Intensity is a power per unit area. Now we're defining something new. It's called the intensity level. So it's a different measure of the intensity. And the intensity level is denoted by the Greek letter beta. It's equal to 10, the number 10. This dB stands for decibels. Times the logarithm, and this is a log base 10. When you use your calculator to do these, you're going to have to use a log base 10. Sometimes some calculators write the log base 10 as just log, or others write it as log base 10. The other kind of log is a log base e, and that's sometimes normally written as ln. So we're not going to be using log base e. E is 2.717, etc. We will be using log base 10 for these kinds of calculations. And it is the log of the ratio of the sound intensity measured in watts per square meter, power per unit area, power in watts, area in meters squared, divided by a reference intensity, also in watts per square meter. And normally, the standard choice for this reference intensity is this threshold of hearing. It's this number right up here. 1 × 10⁻12 watts per square meter is generally used as a reference intensity, but you can use other references, and we'll show you in the next example about how to do other references. So the standard choice is the threshold of hearing, but this concept 16-11, can be used to do any others. So now, knowing the properties of the logarithm, and it may have been a while since you've thought about logarithms, if I equals I naught, so this is the same as this. So if the sound intensity that you're considering is equal to the sound intensity of the reference, then I divided by I naught will be 1. And the log of 1 is 0. So that's this case here. If I equals I naught, then beta will be 0. Sound intensity level. What if I is greater than I naught? That's the next most important one. If I this I maybe is 10 times greater than I naught, then you'd be taking the log base 10 of 10, and that's just 1. And then you'll be multiplying by 10 here, and that'll give you 10. So in that case, beta is greater than 0. If I is less than I naught, then beta will be less than 0 because you have a numerator that's less than the denominator. If you remember the log function, it looks like this. So this is log of x versus x. If x, meaning, in this case, x is representing I over I naught. If I over I naught is greater than 1, then we're up in this region, and the log is going to be positive. And that'll say that beta, the sound intensity level, is positive. Whereas if x is less than 1, we get negative. Okay, here's some typical sound intensities, and this is using the reference of 1 times 10 to the minus 12 watts per square meter as the reference. The threshold of hearing, where you can just barely hear, is 0 decibels. That's where I is equal to I naught and beta is equal to 0. As you get up to higher and higher levels, a live rock concert can be around 120 decibels. That's starting to get painful, a threshold of pain, and here's some other. So this is, as we talked about, this is intensity, the threshold of hearing. As we increase the intensity, then we increase the number of decibels. And here's a rule of thumb. If you multiply the intensity by 10, so if we go from here to here, to go from 10 to the minus 12 to 10 to the minus 11, you can do that by multiplying by 10. Well, what happens to the sound intensity level in that case? It goes up by 10, but it's adding it. You add 10 decibels to the intensity level. Same thing, you go to the next step, multiply this by 10 to go from 10 to the minus 11 to 10 to the minus 10. You add 10 here to get from 10 to 20. That's how that works. And this scale is useful because for those of you that are going to go into speaker design and that sort of thing, the smallest change in loudness that an average listener can hear is about 1 decibel. So you might be able to hear the difference between 65 decibels and 66 decibels. That's about the range that you can detect. So based on that rule of thumb, software is used to amplify a digital sound file on a computer by 20 decibels. By what factor has the intensity of the sound been increased as compared with the original sound file? Well, each time we add 10 decibels, then we have to multiply, so this is for the intensity level, we have to multiply the intensity by 10. And if we add another 10 decibels to make 20, then we have to multiply by 10 twice. So to go up by 20 decibels, we have to multiply the intensity by 100. And so the answer is E here, to change the intensity by 100. Here's another example. I think I'm going to save this one and do it live in class. Actually, I'll take it back. I'm going to do it right now. Audio System 1 produces a sound intensity level of 90 decibels, and this will help you on some of the homework problems. And the System 2 produces an intensity level of 93 decibels, and we're interested in determining the ratio of the intensities. We're going to have to do some math on this one. So the beta is 10 decibels times the log, base 10, of I, the intensity that we're interested in, divided by the reference intensity. So what do we know? Well, 90 decibels, and a system 2 produces a decibels of 93. So let's think of this as the this is the reference, and this one as the one that I'm interested in. So to get the difference between these two, it'll be 93 minus 90. The difference between these two, 93 and 90, is just 3 decibels. The book actually works this one out in a lot more complicated way. This is a lot simpler way of doing this one. 10 decibels times log of I over I naught. Well, how are we going to solve for I over I naught? That's what we want. We want this ratio of intensities. Well, first of all, we're going to have to isolate the log. And we do that by dividing both sides by 10. 3 divided by 10 is just our old friend 0.3. So now, how do we solve for I over I naught? And the answer is we use the property of the logarithm that anytime you take 10 to the logarithm of anything, you get that thing back again. So the trick here is to say, let's take 10 to the 0.3 power and 10 to the log of I over I naught. That's 10 raised to this whole power here. But 10 raised to the log of something is just equal to that thing. It's a property of the logarithm. 10 raised to a power is the inverse of the logarithm. All right, and so that is actually the answer. So if you take 10 and raise it to the 0.3 power, forget what that number turns out to be, but that is the answer to that problem.